Hi, in this session we are going to discuss a new topic called electric displacement and energy of a dielectric system. Let us first look what is electric displacement, and before going to the energy of dielectric system we have to discuss some small topics like electric susceptibility, dielectric constant, etc. Now, electric displacement has a very great importance in the field of physics. Let us just have a history of what is this D. Gauss's law was formulated by Carl Friedrich Gauss in 1835, but was not published until, meaning that the formulation and the use of D were not earlier than 1835 and probably not earlier than 1860s. The earliest known use of the term is of the year 1864 in James Clerk Maxwell's a paper, A Dynamical Theory of Electromagnetic Field. Maxwell used the calculus to exhibit Michael Faraday's theory that the light is an electromagnetic phenomenon. Maxwell introduced the term D, specific capacity of an electric induction, in a form different from a modern and familiar notations. It was Oliver Heaviside who reformulated the complicated Maxwell's equation to the modern form. It was until 1884 that the Heaviside, concurrently with Willard Gibbs and Heinrich Hertz, grouped the equation together into a distinct set. This group of four equations was known variously as the Hertz-Heaviside equation and the Maxwell-Hertz equation, and is sometimes still known as the Maxwell-Heaviside equations. Hence, it was probably Heaviside who lent D the present significance now it has. Now let us go to the physics part of D. We know that the effect of polarization creates bound charges. So what happens when a charge plus Q is kept at the center of the conducting shell? Obviously, this plus Q charges are induced at the outer part of the shell and the minus Q charges at the inside of the shell. That means charges are displacing through the medium enclosed by the shell to the outer part of the shell. This displacement is irrespective of the medium. So, how can we define this electric displacement? Electric displacement can be defined as the amount of charges that are getting displaced through unit area of the shell. So, for that, consider a shell of radius r, and since the plus charges are at the outer part of the shell, we can define this D as D is equal to Q by 4 pi r square into r cap. And what is this 4 pi r square? 4 pi r square is called the surface area of the shell. So, the electric field inside at the surface of the shell can be obtained in terms of D as E is equal to D by epsilon 0. Now, we will check how can I get E is equal to D by epsilon, E is equal to D by epsilon 0. So, for that I will take our equation D is equal to Q by 4 pi r square into r cap, and this I am multiplying with epsilon 0 on both sides, which is equal to epsilon 0 into Q by 4 pi epsilon 0 into r square into r cap. And we know that from our earlier equations, this Q by 4 pi epsilon 0 r square into r cap is nothing but E, which is equal to epsilon 0 times E is the displacement, electric displacement D. So, from this equation I can obtain the equation as E is equal to D by epsilon 0. Now, let us write the Gauss's law in terms of electric displacement. So, we know that according to Gauss's law, in our earlier form, del dot E is equal to rho by epsilon 0. From where we got this closed integral E dot dA over an area A, dA is equal to integral del dot from the Gauss divergence theorem del dot E d2. Then d2 is the small volume. And we know that epsilon 0 E is nothing but this d. So taking this equation, I multiply with epsilon 0 on both sides, I will get del dot E is equal to epsilon 0 into rho by epsilon 0. So I will get this del dot epsilon 0 into E is nothing but rho. And if it is of free charge density, then I have to put this rho f. So here also I have to put rho f, since only if there is only free charge density, and now which is equal to del dot D is equal to rho f. And this is the Gauss's law in terms of D. So this equation represents the Gauss's law in terms of D. Now let us discuss the electric displacement in a dielectric medium. In a dielectric, there may be free charges and bound charges when it is polarized. That is, P is this polarization vector. So I can write the total charge density as rho is equal to rho f plus rho b, and this rho b is called the bound charges. In the last session, we have obtained that rho b is nothing but minus del dot p. We have derived this for a polarized object. And from the Gauss's law, rho is equal to rho by epsilon 0 is equal to del dot E. And this is the Gauss's law we have derived in the first class. So I can write rho is equal to del dot epsilon 0 into E. Now I can rewrite the equation as epsilon 0 E plus P, that is del dot. I am taking this, substituting these values in this equation. For rho b I substitute minus del dot p, and for rho I will substitute del dot epsilon 0 E. Since there are two factors are common, I can write del dot epsilon 0 E plus P is equal to rho f. And from our Gauss's law expression, I can write del dot D is equal to rho f. This is what we have derived just now. So comparing these two equations, I can find out the relation as epsilon 0 E plus P is equal to D. So this is the connection between the electric displacement and the polarization vector P and E. If it is not polarized, this P is equal to 0. So I will get back my equation as D is equal to epsilon 0 E. So we have obtained a relation between this D, E and P. Now let us check what is the curl of this D. So first of all, we will check it for a vacuum. In vacuum, the polarization P is equal to 0. Polarization P is equal to 0. That means del cross D. So I have to take the curl on both sides, which is equal to epsilon 0 E plus P. So in vacuum P is equal to 0. So we can simply write del cross D is equal to del cross epsilon 0 E. So already we have proved this as del cross E is equal to 0. So in vacuum we can write del cross D is equal to 0. So, this is a property of electric displacement, that the curl of electric displacement in vacuum is equal to 0. Now, we will check what is for a dielectric medium. We know that this dielectric medium P is not equal to 0, that is P is not equal to 0. So, substituting, taking curl on both sides, del cross D is equal to del cross epsilon 0 E plus P, and obviously del cross E is 0 and the remaining will be P is not equal to 0 for a dielectric medium. For a dielectric medium, P is not equal to 0. So, the remaining will be del cross D. So, we have to check what is this del cross P. Now, we have to check for a dielectric medium whether this del cross P is 0 or not. Consider a uniformly polarized dielectric object as shown in the figure. So, I should consider a closed path inside this dielectric medium. So, I will name it as A, B, C, D. So, I have to find out what is del cross P. So, this del cross P I can find out using the Stokes relation, del cross P dA over that area, surface area is equal to closed integral P dot dl, and this is our Stokes theorem. So, according to Stokes theorem, I should go over this path which is equal to A, B, C, D, and this integral I can rewrite as closed integral P dot dl is equal to integral A to B P dot dl plus integral B to C P dot dl plus integral C to D P dot dl plus integral D to A P dot dl. So, I can clearly see that this total integral is 0. That means del cross P is equal to 0, which implies that this curl of D even inside a dielectric medium is 0. So, this curl of D is 0. So, how will we know that how much amount of polarization can be achieved within a dielectric medium? As we know, when a dielectric field is applied for a dielectric medium, the charges reorient themselves so that the dielectric as a whole becomes a dipole. So, the dipole moment of a dipole is given by P is equal to alpha E, where alpha is called the polarizability. As we know, the polarization is defined as the dipole moment per unit volume, and if there are n dipoles, then P is equal to n into P. So, P can be rewritten as P has the polarization has the new expression as epsilon 0 chi E into E, and this chi E is called the electric susceptibility. Is called the electric susceptibility. So, we have to define what is this electric susceptibility, and similarly we have this electric susceptibility is the amount of polarization that can be achieved for a dielectric medium. Now, for an anisotropic medium, chi E will be the susceptibility tensor. As we have discussed this polarizability as the polarizability tensor, here for an anisotropic medium, chi E will be the susceptibility tensor. So, how can I write this equation? So, I can write this equation as for an anisotropic medium, P is equal to epsilon 0 into the matrix chi E xx chi E xy chi E x z. Now chi E y x, chi E y y, chi E y z, and here chi E z x, chi E z y, and chi E z z. And this is the susceptibility tensor matrix, and which is into epsilon 0 into E x, E y, and E z. Similarly, I have to rewrite this P also. So, I have to rewrite this P as Px, Py, and Pz. So, this is for an anisotropic medium. So, this is for an anisotropic medium. Now, let us derive what is the relation between this susceptibility and the dielectric constant. Since we know that d is equal to epsilon 0 E plus P and P is equal to epsilon 0 chi E into E, and so I can write d is equal to epsilon 0 E plus P and P is equal to epsilon 0 chi E into E. I will substitute this P in the first equation, which will give you d is equal to epsilon 0 E plus epsilon 0 chi E into E. But we know that for a dielectric medium of having absolute permittivity epsilon, we can rewrite d is equal to epsilon E. This is for the case of vacuum. So, which is equal to E into epsilon into E is equal to epsilon 0 E plus epsilon 0 chi E into E. Here this E are common. So, we will get epsilon is equal to epsilon 0. So, common. So, I can write epsilon 0 into 1 plus chi E. And this epsilon by epsilon 0 is equal to 1 plus chi E. And what is this epsilon 0 by epsilon 0 is the relative permittivity epsilon r or k, and which has the relation 1 plus chi E. So, this is the relation between the dielectric constant and the electric susceptibility. So, the effect of introduction of a dielectric medium in free space can be explained with the help of this equation for K. Now, let us derive what is the energy of such a dielectric system. We know that the energy of an electrostatic system in vacuum is given by W vacuum is equal to half into integral epsilon 0 E square d2. So, this we have derived that work done for a vacuum is equal to half into integral epsilon 0 E square d2, and this is for case of vacuum. So, when a dielectric medium of constant K is introduced, then this epsilon is the absolute permittivity of the medium. So, if it is the absolute permittivity, I can write W of dielectric is K times W of vacuum. This is K times W of vacuum. So, what is this W of dielectric? What is the W? W is the work done or the energy of that dielectric system. So, on replacing the equation, W of dielectric is equal to half into K times integral epsilon 0 E square d2. And what from our equation K is equal to epsilon by epsilon 0. So, we will get epsilon 0 into K is equal to epsilon. So, the work done for a dielectric medium or the energy stored in a dielectric medium can be rewritten as K into epsilon 0 is epsilon, which is equal to half into integral epsilon E square d2. but this E square is nothing but half into integral epsilon into E dot E d2. And what is this epsilon into E? Epsilon into E is called the D. So we have the expression for work done for a dielectric system is integral D dot E d2. So this is the work done for a dielectric system. Now let us consider a plain parallel capacitor. For such a capacitor, we know that Q is equal to C vacuum into V. If the capacitor is filled with dielectric medium of absolute permittivity epsilon, the equation for C dielectric is equal to epsilon A by D. So we will get C of dielectric is equal to K times C of vacuum. This is a simple derivation. We know that C vacuum is equal to epsilon 0 A by D. If I fill this space completely with a dielectric medium of absolute permittivity epsilon, the new capacitance, which I call C dielectric, is equal to epsilon A by D. So dividing these two equations, I will get C dielectric is equal to K times C of vacuum. K times C of vacuum. So that means the capacitor with a dielectric can store more charges. So the work done to store such amount of charge can be derived as W vacuum is equal to half into C vacuum into V square, and we will get back that equation as W of dielectric is again, and we know that W of vacuum, the work done to store that charge for in the case of an capacitor is C vacuum is equal to half CV square. So instead of C vacuum, so for work done for a dielectric, I have to substitute half into C of dielectric into V square. So since we know that this C of dielectric is W of dielectric is equal to K times W of vacuum. This was the result we obtained just before. So this is also true for a capacitor which filled with a dielectric constant K. Now consider a sphere of radius r, which is a linear dielectric material placed in a uniform electric field E0. We have to find out what is the electric field inside the sphere. We will discuss this important problem in the next session. In this session, we have discussed the concept of electric displacement and energy of a dielectric system, and also the energy stored in a capacitor. Also, we have derived the Gauss's law in terms of electric displacement. So at a glance, we obtained the equation as del dot D is equal to rho f, and this rho f is called the free charge density, and D, we got the expression connection between this electric field and the electric polarization vector P as D is equal to epsilon 0 E plus P. For a uniformly polarized dielectric object, curl of D is equal to 0, and this dielectric constant and electric susceptibility K is equal to 1 plus chi E, and we obtain the energy stored in a dielectric is K times the energy stored in vacuum. And for a capacitor having dielectric medium, the work done for dielectric is equal to half into C of dielectric into V square. And also we have a connection between this energy stored and the electric displacement and electric field E as W is equal to half into integral D dot E d2. And thanks for watching this session. Hope to see you soon.